Jenker gas calorimeter used to find out the high calorific value of gaseous fuel. It is it is study type temperature, the various spots in calorimeter shown in figure. You see the diagram. Jenker gas calorimeter, gas meter, pressure regulator valve and condenser, water inlet, overflow, some air gaps are there, burner, this is candle is there, combustion products and combustion chamber, water outlet and air gaps and thermometer and water outlet. In this figure, um, so there is a general gases. There is a gas meter. There is a and pressure of regulator. In this condition, gas is only. There is a complete combustion products are outside. There is a water is cooling and water inlet. There water supplied there. In this condition, then the out thermometer is maintained the regulating of the temperature. These are the temperature. You see the diagram. In Jenker gas calorimeter, the Jenker gas calorimeter is to find out the high calorific value of gaseous fuel. Instead, it is study flow of gas calorimeter. And description of the gas calorimeter. Jenker gas calorimeter consists of inner combustion chamber and which is product of the combustion of move upward direction and this chamber is surrounded by the water jacket which chamber of tubes and flues passes through. Heat liberated by the combustion of the gas is absorbed by the water. Thermometers are provided by calorimeter to measure the exit gas temperature and the arrangement of made up ensures the complete transfer of heat absorption combustion to water. And the temperature of exit gas is nearly equal to the room temperature. Once again repeat, it is inner combustion chamber, which is product of the combustion chamber moves upward direction. The chamber surrounded with a water jacket, into which number of tubes passes there. Heat liberated with the combustion gas is absorbed by the water. Thermometers are provided the measure exit gas temperature. The arrangement ensures the complete transfer of the heat combustion and the two water and temperature of exit gas nearly equal to the room temperature. Working principle of the Brenker gas calorimeter. In this, the measure quantity of the gas calorific value to be determined by supply combustion chamber of the gas meter and which is measured its volume and it is measured with volume and pressure regulated with regard to the pressure of the gas means by manometer and the water enters the calorimeter under the connection here and the temperature of water entering and leaving and calorimeter noted by the thermometer. So in first inlet temperature is measured, then after exit water temperature is measured. Then the gas is mixed with the sufficient of air burns and the burner and gas and the hard products of the combustion move upward direction to the combustion chamber and move up downward direction through the fuels and finally escape through the exit. And the temperature exit in the record by the thermometer nearly equal to the room temperature. The water moves in a direction and opposite to the hot gases in the fuel. Water moves in this direction and gases move opposite direction and out upper portion, the temperature quantity to be recorded. The water formed by the condensation of the steam collected to be measured, condensation to be measured. Since the process one steady flow of the low velocities, heat loss is lost by the products of the combustion, and that is heat liberated by the complete combustion of the gas is equal to heat gained by the water, and the most of the steam in exhaust gas is condensed. The gas calorimeter therefore measure the high calorific value of the fuel gas. The lower calorific value can be calculated from measured quantity of the steam condensed in the calorimeter. To calculate the high calorific value of the gas must be converted in a stable condition, that is a 15 degrees centigrade and 760 mm of density. Knowing the mass of water flowing and temperature right, the gross calorific value can be obtained by equating of the liberated by the gas and heat absorbed by the water. Heat liberated by gas equal heat absorbed by the gas. Is it clear? Once again, repeat. In this condition, delta gas calorimeter. We explain them simple. In this condition, we have a gas meter. In this condition, gas goes to the pressure regulator valve to this pump burner to some current. In this water inlet in overflow, there is a constant head process. And in this condition, thermometer is there. In the water in this direction is more. Gas is moving in this direction. And gas is burned. Heat in this gas combustion process taken on. In heat liberated by the combustion process, there is a water is absorbing there. In this condition, fuel is burned, uh, gas is burned. There is a one gas is there, unwanted gas is moving in this condition, and water is moving in this condition opposite direction. First condition, you take the water inlet temperature. You find out that in this gas meter is there. There is no quantity of the volume of the gas is mass of the gas is known, and pressure regulator valve is maintain the pressure is constant. The burner, then moving of the gas, supply the gas. They come. There is some amount of fuel is air gas is burning, yeah, gas burning. This is some air gap is maintaining. This is in this condition, in the fuel is burned, then combustion take this combustion products are moving to outward direction, and exit gas is outward direction. There is just um, some amount of heat is absorbed by the water after complete combustion is taken. First initial condition, there is a T1 is noted. After combustion is taken, thermometer measures the T2. In this condition, T2 find 52 is find out. Then there is the same process in SCV and LCV volume. For let P naught is a standard to 760 mm of oxygen. T naught is a standard temperature is 15 degrees centigrade converted into 288 Kelvin. The volume of the one gas is HSTP condition, and P1 is the pressure of the gas in mm of oxygen. HW plus 13 plus 6 is H0. HW is the manometer reading in mm of HT. XB is a barometer reading in mm of HG. The working procedure is V1 is a volume of gas and one recorded with the gas in meter. Then T1 is the temperature of the gas at inlet Kelvin degrees, and CW is specific heat water at a 4.18 kilojoule per kg Kelvin. M is capital M is the mass of water collected in case. SCV is a high calorific value. Then working principle we know that P naught V naught by T naught equal to P naught V1 by T1. V naught equal to P1 V1 naught by P naught. That by T. Assume that no heat loss. Heat absorbed by the water and chlorine. V naught into SCV MCW T2 minus HCV equal M into CW T2 minus T1 by V1. Once again repeat. The consists of cylindrical components surrounded by the water jacket. The water jacket is made of a number of tubes through a water flows in upward direction. The initial and final temperature of the water and gas is recorded by the thermometer. A gas meter is provided to supply the measured quantity of the fuel. The pressure of the regulator is provided to control pressure of the gas is supplied. Working principle of the measured quantity of the meter cube of gas is applied to the combustion chamber. The pressure of the gas is measured by manometer, controlled by the pressure and regulator. The gases of fuel combined with sufficient air burns with the burner. The combustion gas is first moved upward direction and then moved to the downward direction to a tube surrounded by the water jacket before the leaving from the exit. The water is supplied to the calorimeter under the constant heat, and the water of the gas flows opposite direction. Water of the maximum heat transfer. The temperature entry to exit. The water gets second by thermometer. The temperature of the gas leaving the calorimeter at almost room temperature. The water formed due to condensation steam connected to measure. As more steam is exhausted to gas condensed with the high calorific value. The low calorific value can be found from the measured quantity of the fuel condensed to the calorific value. The value of HCV fuel can be calculated by the converting of the volume of the gas from HPP condition at 15 degrees Celsius 760 mm of HG. Then P naught is a standard pressure at 760 mm of HG. T naught is a standard temperature at 288 Kelvin. V naught is a volume of one gas at STP condition. T1 is a pressure of the gas, and what HW is a water manometer reading at in mm of water. HP is a barometer reading. V1 is a volume of the gas recorded by the meter. T1 is a temperature of the fuel gas in the inlet. And CW is specific heat of water 4.187 kilojoule. M is the mass of water. It's a electric volume. We know that the P naught V naught by T naught equal P1 V1 by T1. P naught equal P1 V1 by P naught into T naught by the heat equal to the gas equal heat absorbed by the gas water and calorimeter. We probably call it CV plus MCW T2 minus 1 by V1. So we see the diagram once again. Some air gap there. The gas calorimeter pressure, pressure regulator valve induce some amount of burner, supply the gas, then come apply the gas. The water inlet is water constant water and is what is supplied in this direction. And first in this condition measure the temperature in thermometer. So in this burning of the gas, complete combustion takes place. Gas are moving upward direction through tubes. In this exhaust gases are exiting of the outward direction. After combustion takes place, you measure the temperature in thermometer. We are like room temperature. Some amount of gases are condensation is take place in LCV volume. Condensation due to LCV local calorific volume. In this condition, water in water in moving upward direction, and in this gas is complete combustion gases are moving up first in this upward direction, then move to the downward direction. In this condition, first you measure the known quantity of the known quantity of the gas volume is known. You find out the initial temperature, you measure the initial temperature, final temperature at STP condition, at room temperature, standard temperature conditions. Is it clear? We go through the calculation. Is it clear? We go through the some amount, some problems. The following result of the were obtained during the test conducted by the sample of coal using of the bomb calorimeter. Mass of coal burn 1.1 gram, mass of water calorimeter 2.5 kg, and initial temperature of the water 19.4 degrees, final temperature 23.1 degrees centigrade. Water equivalent of the calorimeter 0.04 kg, assuming a specific heat of water 4.187 kilojoule per kg. Find the HCV of the coal. If the coal contains 8% of H2, calculate the LCV of the coal. So once again repeat. The following results are obtained during the conducting the sample of coal is a bomb player. Mass of coal is 1.1 gram and mass of water in calorimeter is 2.5 kgs. And initial temperature of water 19.4 degrees centigrade. Final temperature of water is 23.1 degrees centigrade. And water equivalent of the calorimeter 0.04 kg. Assuming a specific heat of water 4.187 kilojoule per kg. Find the HCV of coal if the coal contains 8% of H2, calculate the LCV of the coal. So in this condition, all the data you can find out the HCV. Given data, mass of coal M equal 1.1 gram, you converted into gram into kilos, 1.1 by 1000, 0.0011 kg. Then mass of water in calorimeter, capital M equal 2.5 kg. Water equal to calorimeter M equal 0.4 kg. Initial temperature of water T1 equal to 19.4 degrees centigrade and final temperature of water 23.1 degrees. Specific heat of water 4.1875 kilojoule per kg. Mass of hydrogen HCV equal to M into M into MC into CW into T2 minus T1 by cap smaller. HCV equal to M plus M into M plus C. PW to M 2.5 into 0.4 into 4.187 into 23.1 minus 19.4 by 0.0011. You get calculate HCV equal to 40,842. You go to LCV equal to LCV into HCV minus 9 is 22,442. LCV equal to 40,842 minus 9 into 80%, 80.0.8%, 8 by 100, 0.0242. That LCV equal to 40,842 minus 1754, 39.084 kilojoule per kg. Once again, we can you know all the values. The conversion is the 1.1 gram converted into kg, 1.1 by 1000, 0.011 kg, M equal to 2.5 kg, MC equal 0.40 kg, T1 equal 19.4 degree, T2 equal 23.1 degree, TW equal 4.187 kg, ST equal 0.08 kg, SCV equal to M plus MCT2 minus 7 by 2.5 in plus 0.4 into 4.187 into 23.1 minus 19.4 by 0.01 by get a 40.842 kilojoule per kg. LC of the core Let the LCV is a lower calorific value of the LCV equal LCV minus 9H2 into 2442. LCV equal to 40,842 minus 9 into 0.08 into 24 into LCV equal to 40,842 minus 175 plus 39.084. We go to the another problem. A bomb calorimeter is used to find out from the calorific value of sample of the following data recorded during the test. Mass of coal 1.15 gram. Mass of the fuel 0.05 grams. Calorific value of the fuel is 6,000 kilojoules per kg. And mass of the water in calorimeter 3 kg. In water equivalent apparatus 0.6 kg. And temperature of water before ignition 18 degrees centigrade. Maximum temperature of water 21.5 degrees centigrade. And cooling correction is 0.016 degrees centigrade. Hydrogen content of coal 4.3% and calculate the HCV and LCA of the fuel. Once again, repeat which where is given. A bomb parameter is used to find out the calorific value of the sample of coal. The following data recorded during the test. Mass of coal 1.15 gram. Mass of the fuse is 0.05 grams. And calorific value of fuse is 6,000 kilojoules per kg. Mass of water in kilometer 3 kgs. Water equivalent apparatus 0.6 kgs. Temperature of water before ignition 18 degrees centigrade. And maximum temperature of the gas is 21.5 degrees centigrade. Then cooling reaction 0.016 degrees centigrade and the hydrogen content of the core is 4.3%. Calculate the CV and LCV and given data mass equal to 1.15 grams, 1.15 by 1000, 10 power minus 3, there is 0.00115 kg, and mass of the fuse were FW equal to 0.05 gram into 0.05 into 10 to the power minus 2, 0.00005 kg. Calorific volume is equal to 6,000 kilojoule. Mass of water equivalent. Cap chemical 3 kg. Water equivalent in kilometers equal 0.6 kg. Initial temperature of water T1 equal to 18 degrees centigrade. Final temperature of water T2 equal to 21.5 degrees centigrade. Cooling react correction T is equal to 0.016 degree. Hydrogen now content in coal HT equal to 4.3 kgs. Equal to 4.3 by 100 that is 0.043 kg. Then LCV high calorific value of fuel assume the specific heat of water 4.187 kilojoule per kg. We know that the M into HCV, MFW, MFW into CV, capital M plus MC, CWT2 minus T1 plus TC. The TC is a cooling reaction 0.00115 into HCV plus 0.0005 into 6000 into G3 into 0.6 into 4.187 into 21.5 minus 18 plus 0.016 in 0 hence 0.0115 plus HCV 0.3 that equals 3.6 into 4.187 into 3.516 SCV equal to 53 minus 0.3 by 0.00115 SCV equal to 45,826.8 kilojoule per kg. LCV lower calorific value of coal equal to LCV equal to SCV minus 9H2 into 2446 into LCV equal to 45,2823 minus 9 into 0.043 into 2446 LCV equal to 45.2823 to 8 equal 44,816. Once again repeat. A bomb calorimeter is used to find out the calorific value of the sample of the coal following data recorded during the test. Mass of the coal 1.15 gram, mass of the fuse value 0.05 grams. And calorific value of the fuse value 6,000 kilojoule per kg. Mass of water in kilometer 3 kgs. And water equivalent apparatus is 0.06 kg. And temperature of water before ignition 18 degrees centigrade. Maximum temperature of the water 21.5 degrees centigrade. Cooling correction is 0.016. Hydrogen of the content of the coal 4.3. Calculate the SCV and LC of the fuel. And given data is given, mass of the coal burn 0.015. They converted into kgs 1.15 into 10 to the power of minus. You go through the m equal 1 0.0115 kg. Mass of fusel input 0.05 grams. The 0.05 grams converted into kilograms. Kgs 0.05 into 10 to the power of minus 10. That is a 0.0005 kg. And calorific value fusel are equal Cv equal 6000 kilojoule per kg. And mass of in water 3 kg. And water equivalent temperature thermometer MC equal to 0.06 kg and initial temperature T1 equal to 18 degrees centigrade and T2 equal to 21.5 degrees centigrade and Tc equal to 0.016 degrees centigrade. Hydrogen concentration of H2 equal to 4.3%, 4.3 by 100, that is 0.043 cases. And let HCV equal to high calorific HCV equal to high calorific value and assume the specific heat of water CW equal to 4.187 kilojoule per kg. Heat liberated by the burning coal equal to heat absorbed by the water and calorimeter. M into SCV plus MFW plus CV equal to M into capital M into MC CW T2 minus T1 plus Tc. This is a cooling reaction. This is a cooling reaction. 0.00115 into SCV plus 0.005 into 6,000 3.3 plus 0.6 into 4.187 into 21.5 minus 18 plus 0.016 equal to 0.0015 into SCV 0.3 into 4.187 into 3.516 SCV equal to 53 minus 0.3 into 0.00115 equal to SCV equal to 45,826.8 kilojoule per kg. We go to the LCV. Lower calorific volume. The goal we know that the LCV equal to SCV minus 9H2446. LCV equal to 45,823 minus 9 into 0.043 into 2446. LCV equal to 45,823.8 minus 954.342. LCV equal to 44,869 kilojoule per kg. We go to another graph, Junkers gas calorimeter. The following figures were obtained during the test on coal gas using Junker gas calorimeter and volume of the gas sample is 0.036 meter cube and mass of cooling water is 14.1 kg and pressure of the gas 82 mm of water, barometer reading 750 mm of oxygen, temperature of gas 31 degrees centigrade, initial temperature of water is 26 degrees centigrade. Temperature of the outlet 38 degrees centigrade. Mass of the steam furnace 35 grams. Standard barometer reading 760 mm of oxygen. The standard temperature is 15 degrees centigrade. Determine SCV and LCV of the coal gas. Once again, reading. The following results were obtained during the test on coal gas Junker gas calorimeter. Volume of the gas sample is 0.036 meter cube and mass of the cooling water is 14.1 kg and pressure of the gas is 82 mm of water and diameter reading is 850 mm of oxygen. Temperature of gas 31 degrees centigrade and temperature of the 31 degrees, initial temperature of 25 degrees. Temperature of water 38, outlet is 38 degrees. The mass of steam contains 35 grams and standard barometer is 760 millimeters. Standard temperature is 50. Determine the CV and LCV. So volume of the gas NTP condition V1 equal to 0.0 is given. Temperature T T1 is a 31 degrees converted to Kelvin. T31 plus 273 304 Kelvin. Mass of water circulated, capital M equal to 14.1 kg. Initial temperature of water T1 equal to 26 degrees centigrade and final temperature of water T2 equal to 38 degrees. Then manometer reading HW equal to 82 mm of water and barometer HB equal to 750 mm of HB. The mass of steam furnace MS equal to 35 grams. The 35 grams is converted into kilogram. 35 into 10 to the power of minus 0.035 kg. The standard pressure is 760 mm of the standard temperature 15 degrees centigrade. 15 plus 273 is 288 Kelvin. Then FCV of the coal gas, high calorific of the gas. Now absolute gas P1 equal to HW 13.6 plus HB. P1 equal to 82 plus 13.6 plus HG. H 750 equal to 756.03 mm of Hg. Is it clear? Then the volume of gas reduced to HTP condition by the equation. P naught V naught by T naught equal to P1 V1 by T1. Is a V naught equal to P naught V1 by T1, the T naught by P naught. The V naught equal to 756.03 into 0.036 by 304, 288 by 760. You get V naught equal to 0.034 meter cube. Assume the specific heat of water Cw equal to 4.187 kilojoule per kg. Cv of coal gas M into Cw T2 minus T1 into V0 kilojoule per meter cube. HCV equal to 14.1 into 4.187 into 38 minus 26 by 0.034 meter cube kilojoule per meter cube. There is 20.836 4.8 meter kilojoule per meter. We go to the LCV. Let LCV equal lower calorific volume of the fuel. LCV equal LCV minus MS into L is the latent heat of water. At 20.8, 20,836 minus 1, 36.48 minus 0.035 into 2400. 20,836.48 minus 86.3. You get LCV values 20,750.18 kilojoule per meter cube. Once again, look here. There is a standard is given. There is a absolute temperature of the gas P1 equal to HW water head plus 13.6 into HB. You get 82 mm of water, 13.6 convert 750 is a mercury converted into pressure head. This is 756.03 mm Hg. The volume of STP condition P naught T naught P naught V naught by T naught equal to P1 V1 by T1. V naught equal to P1 V1 by T1 by T naught by P naught. In this condition, 7 is P naught V1 equal to 156.03 by into 0.0 by 304 into 288 by 7 you get V naught equal to 0.034 meter cube. Assuming specific heat of water equal to 4.187 HCV of coal gas M into Cw T2 minus T1 by V naught. HCV equal to 14.1 into 4.187 into 38.26 by 0.034 with HCV equal to 20.836.48 kilojoule with LCV equal to SCV minus MS into LL is a Latin name 20.836.48 minus 0.035 into 2466. LCV equal to 20,836.48 minus 86.3. LCV equal to 20.750.18 kilojoule per cube. In this way, we have learned how to solve the problems of the bomb calorimeter, Jenker gas working for the Jenker gas calorimeter. Explain the working principle. We do the sum. The Jenker gas will find out the HCV of gas also. HCV of the gas is fuel and LCV of the gas is fuel, HCV of the solid fuel, HCV of the gas is fuel. Is it clear?